Welcome to those of you in the room with us, and welcome to those online. This is the 5th of our webinar series on all of our code clauses, or in particular 5 special code clauses that we've picked out. What I would like to do is just cover just the normal stuff around CPD points and NZRAB. So those points are loaded if you've registered with us, and you can log your LBB points for yourself if that's for you. I just wanted to start with a comment. At 7:23 last night, I got an ad through from, I think it was a Certified Builders magazine, and in that it had this ad for Jib, and it said, designing to E3 internal waterproofing. I thought, that's new. I didn't know it was called that. E3 internal waterproofing. Now, I'm not mocking Jib, but it's very, very specific about bathrooms, and that's kind of what we're here today to unpeel, is to say, hang on, it's not just about bathrooms. It's not just about laundries. That's what Ben, who I'll introduce in a moment, is going to talk to us about. But then I got this other, well, I was listening to the radio this morning, 7:15 on the way into work, and an ad came on for Shower Dome. Now, who's heard the ads for Shower Dome? You guys in the audience here? Right. You know, I actually like Shower Dome. They actually work. The physics is really good. It's actually really sensible. But the next part of the ad kind of irritated me. It says, you don't need a fan, an extract fan. I thought, well, that doesn't really go very well with G4 ventilation requirements. So what I want to point out just in that is there are lots and lots of conflicting bits of information which don't come together really, really well for us as designers, for us as builders, and that's a problem, and that's what we're trying to give a nudge towards fixing. Now, in that time, my iPad's turned itself off. What I want to do is introduce our 2 panelists for today. So they're on screen here beside me, and if you're online, you can see them anyway. So we've got Simon Cater, who is Auckland-based, and Richard Hollard, who is also Auckland-based, and they are going to be pulled into the panel questions. If you've been part of our webinar series, you know how that works. They're also going to be available for the Q&A at the end. Thanks, guys. We'll catch you in a bit. Now, they are not going to answer the first poll question. Ben's going to answer the first poll question. And Ben Ingledew is our presenter today. He is all the way from North Yorkshire.
Correct.
But he arrived in New Zealand in 2001 after finding somebody to love. And now he has 2 little children, very little. It's quite amusing when Ben and I work together. He's sitting in Christchurch in his office, and he's on noise cancelling headphones, which means I can hear, but he can't hear his 2-year-old, Daddy, Daddy, except it doesn't sound like that. It sounds more British.
Much cuter.
Yeah, okay, and cuter. Thanks, Ben. But it's quite a funny experience to be working with Ben when he's in his office there. Now, Ben is a builder, a trade, qualified builder, about 7 years, 8 years on tools. He's also a qualified teacher, 15 years teaching. He's also, I discovered this morning, actually listening to, as a fluent Swiss German speaker. Now, his Swiss German's quite good, but his English is a bit average. So in his presentation, he uses the word Petri when he actually is trying to say Petri dish.
Okay.
And I think there's another couple of words there. You might just, listen out for those as we go. Yes. But without further ado, Ben, we look forward to your presentation, and I'm going to wait here because we're going to do the poll question almost instantly. Oh, I was just going to mention, before I hand over, what we have covered are just 5 of the code clauses. So B1, we've did that deliberately because that's kind of the first one you start designing with. Structure, B1 structure. Then you think about the durability of what you're designing with, so that kind of comes second. It sort of sits on top. If you mess up durability, you have issues with B1 structure. And then we looked at E2, outside the building, external moisture. If we do a good job of that, B2 durability is less of a drama. B1 is good. We keep the building standing up. Can you see how they connect? And if we stuff up E2, if we get that wrong, which we have done in the past, we all know that, B2 durability becomes a problem and we have an issue with B1. And that's how we've tried to work this whole series. So then when you add insulation, which we did 2 weeks ago, we talked about H1 energy efficiency and specifically how energy was being used in a building and how we can change that, so how we can reduce the amount of energy being used in the building. That is through the use of insulation and some other bits, but insulation is the biggie. If you put moisture into that space, meaning if you mess up E2, or as we're going to see today, if you mess up E3 and let moisture into that space, you're not just affecting the energy efficiency of that piece of insulation, if you like its effectiveness. You're messing up, you're in the frame now, so you're messing up B2 and you've messed up B1. So all of those things we've just tried to connect, and we're not trying to do that in any flash way. We're just saying, here's what happens, here's the consequence. So today, Ben, we get to E3, internal moisture, which you're going to take it away. It has the same wording as E2. I look forward to what you have to say. Poll question.
Yep. Thanks, John. Appreciate it. Thanks, and thanks for coming today. Thanks for that introduction. And welcome to everybody here. It's really lovely to have a live audience. When we do these online, it's very different. You're just talking to yourself in the camera, and it's a little bit spooky, but it's really nice to have you guys here. So thanks for coming today. We are going into the first poll, and so for you here, that's just a show of hands. I'm trying to get you thinking about what we're hoping, or what I'm trying to get you to think about. I'm trying to get your brain into that gear. So which area of the homes does E3 apply to? So those of you online, get ready to start clicking as well. I'd like you to have a good think about this, please, before we unpack it.
Great. Okay, so we'll just quickly roll through those. So the question is, which areas of the home does E3 apply to? Does it apply to kitchens, bathrooms, and laundries only? All habitable spaces? Answer C is roof spaces and basements, and D is sweaty teenagers, bedrooms mainly, which I think is actually quite a good answer.
Yeah.
So those are the questions. Now, for those online, you guys can enter your answer there, and I'm going to roll through those questions just quite quickly, just with an ABCD for our audience in the room here, and I'm going to try and take a bit of a swipe, bit of a guess at how at the percentages of those guesses as we go through, because it is all guesses, eh? And we don't know this stuff yet. All right, so who thinks in the room, kitchens, bathrooms, laundries, who's got A as their only? Yep, okay, so we've got one in there. Yep, you can be brave, come on, we're with friends, and we've got beers afterwards, so it's all good. B, all habitable spaces. Ooh, okay, so I'm gonna say at least 90% of the room have got that one. C, roof spaces and basements. It's not exactly credible, but it's still, I guess, important to think about. And I think D is actually the right answer, sweaty teenagers, bedrooms mainly. Anybody want to go for that one? Thanks, Dirk. Thank you. One of our team, just because he's being brave. All right, and what we'll do is now we'll turn to look at what the answers were online at that too. So 20% said A, kitchens, bathrooms, laundries. 80% all habitable spaces, and nobody brave enough to choose the sweaty teenagers. Why would you? All right, Ben, I'm going to leave that with you and to get into your presentation.
Thank you. Thanks, John. Yeah, most people in here also said habitable spaces, and that's absolutely right. It's really important, though, just to get your head into the right gear. We are dealing with the whole home, and that's really important. What we're going to do in this presentation is divide into three parts. We've got the context and the history and some of the background of what E3 is about. So that's our why. Why on earth should we be thinking about internal moisture? Then we're going to have a look at the drive-by design. So part two is about trying to design out the risk of internal moisture. So what design aspects can we throw at our solutions in order to reduce the risk of condensation, mold growth, etc. And then the last part, we're looking at the what. What can you use and what can be done in terms of and what equipment can we use when it comes to building it tight and ventilate right. Yep, come in, guys, find a seat. We're broadcasting live, but that's okay. In you come. Okay, clause E3, internal moisture. Yes, it is. It's not just bathrooms and kitchens. Now, the alternative solution for E3, all it does is offer us acceptable solutions for drips and leaks. That's what most of it's talking about. So surely there's more to it than that. And as John said, I actually spent 15 years as a primary school teacher, and it introduced me to many a naughty child. And they would sit at the back, disrupt the class, spread their malevolence, and cause damage wherever they could. These naughty children, though, were often all they were doing is looking for acknowledgement and some kind of affection. So if you can develop a relationship with those naughty people, if you can give them the time of day and show some kindness, learn to understand them, then you can learn to understand their problems, and they can also become a very successful member of the classroom and also go into great things. Now, the naughty child of E3 is just the same. If we don't give it the attention it deserves, it's going to cause problems further down the track, and it's going to give us headaches into the future. If we don't give E3 the attention it needs and apply some knowledge to it, the mold will spread through our homes, and the debilitating conditions that come with that are causing us enormous problems: asthma, inflammatory responses, poor attendance at work and at school. So the naughty little Johnny from E3, we need to look after. Come in. So let's give it a little bit more attention. Come in and find a seat. Now, if we look, the E3 and the clauses are broken down into 3 parts. We have the objective, the functional requirements, and the performance. The objective is pretty clear. We need to safeguard from the accumulation of internal moisture. That's the objective of E3. Safeguard from the accumulation of internal moisture. To reduce the risk of fungal growth in all habitable spaces. Well, if that's the case, why aren't we doing it? Why are we just hoping that steel framing without thermal breaks is going to work? Why are we just bandying it around and thinking, oh, well, it'll be okay? Now, there's a big problem with this. Just like the naughty child that's in the classroom, if you ignore it and wait for it's somebody else's problem. And as a teacher, I know I'm guilty of doing that. You have that kid that sits at the back and you think, no, it's term 2. I'm probably not going to change him. Term 3, well, it's nearly not my problem, is it? By the end of term 4, wait till Mr. Jones gets him. And that's what we're doing with the problems when it comes to mold in our homes. We're making it, the designer pushes it onto the builder. The builder pushes it onto the homeowner. And by the time it's a problem for the homeowner, well, who's accountable then? Oh, that's because you're not using the home correctly. That's because you don't use the home right. Oh, so it's the homeowner's responsibility now to meet E3. So although the code knows all about little Johnny, naughty little Johnny in E3, we still have not adopted a verification method. There is no specific method adopted. We are using a trial and error approach. We are waiting to see what happens. Or let's put the steel beam in and hope it'll be okay. Or let's use this framing. Let's just use 90 mil of insulation. The trial and error method is proving not to work though, and we are getting mold in our homes. Back in the good old days, we would have given Johnny just a clip around the ear and told him to sit down and shut up, all right? But thankfully, lots of things have changed. Back in the good old days, we also lived very differently. And usually there was someone at home and the home fires were burning. New Zealand had a solid fuel dependency. We were burning coal and wood in our homes across the whole nation. Thankfully, that has also changed. The air is much cleaner as a result. I live in Christchurch, and pre-earthquake, you could see the smog thick across the environment, and you could see it thick lying low. And now the air is much, much cleaner because we're not allowed to burn solid fuels. But as a result, our homes are now getting stale air trapped inside them. And that's because the fires are drawing out, which we'll have a look in a minute. When you have a look at this floor plan of a 1950s villa, and I love the word villa because it's very romantic, but when you actually go and start flatting in a 1950s villa, there's nothing very romantic about it at all. It's extremely cold and uncomfortable. You can see there that the wash house, top left there in the image, the toilet, the bathroom is actually outside the thermal envelope. So there's a floor plan on the left of the picture there. You've got the kitchen, the bedroom, the dining rooms. The living spaces are inside that thermal envelope. And that was the way we used to live. But of course, it's the way we still do live. It's very much the floor plan of most people's homes in New Zealand, because not everybody is buying a brand new home. Now, the draw of the fire that was positioned in the kitchen there would suck air through that home. When you burn in a wood burner or an open fire, it needs a huge air supply. And so what it was doing was continually drawing air through any nook and cranny that it could, through gaps in floorboards, through our double hung sash windows, under the door, and it was ventilating as it went the whole time. So the heat inside the kitchen was often unbearable. If you can't stand the heat, get out of the kitchen. It was real. The living spaces were often overheated, while the extremities of the homes were far too cold to sit and snuggle down and read a book. And so the system worked for a while. Now, in our major cities, the use of solid fuel is being banned, and the air is much cleaner as a result, as I said. But the lack of air movement causes an increase in relative humidity, and the mold will take hold. Now, modern homes are built to very different standards, and here we can see the floor plan of the same home. There's no fire in there. The heat pump is somewhere near a living space. The techniques mean that home is more airtight, and this is a good thing. An airtight home is a good thing. It's a bit like having an inner tube of a tire that it needs, if you want to pump it up, and you imagine the heat pump is like the bicycle pump. If you're pumping away and you've got a hole there, well, you just have to keep pumping, don't you? But if you can seal that home up, you're not continually pumping heat in. All right, so airtight homes are good, but what we have to manage is the relative humidity within that home and the air quality. Now, modern lifestyles are also different. The occupants of this $1 million home, which is, I find amazing that would, the average home in New Zealand is $1 million. You get $1 million bucks, you get that. Okay, for $1 million bucks, you get a home like that. But then you've got two people that have to be working long shifts. They're working full time. So they get up in the morning, these two occupants, they both have a shower because they've got to be nice and presentable for work. They then cook their lunches. They then hang up their washing because they're not allowed to put it on the veranda because that's what the covenants say, inside their bathroom, or actually we'll put it in the lounge because it'll get loads of sun coming in. And then they lock all the windows and doors for security, but also for the particle contaminants. They live near a busy road and they don't like diesel dust getting into their homes. So they seal the house up and go to work for 10 hours. Then they come home and they try and they think, oh, it's a bit funky in here, but it's too late by then. The relative humidity is increased in the home. 5 litres have come out of that washing. You think about the weight of dry washing that comes out of a machine. You think about the weight of washing comes out of a washing machine. You hang it up and dry, the weight of that, that's how much water has gone into your living space. People don't like to leave windows open because they don't want it to be cold. They don't want it to be risky. So now the relative humidity is high, and the mold has begun its day's work as well. Mold's really important. It's really important part of our ecosystem. Now these images here, they run through some of our temperatures from newer data, but if it wasn't for mold growing, our ecosystem would collapse. We need mold. It's one of the pioneer plants. Everything starts feeding with that and off that. It's not a plant, of course, it's somewhere between. It's closer to being an animal than it is a plant, actually. If we have a look at the median annual average temperature, that's the map of New Zealand on the left-hand side of your screens. You can see that most of New Zealand is a green colour. That means most of New Zealand is somewhere between 8 degrees Celsius and 14 degrees Celsius. That's over 24 hours, 365 days. There's only one little place way up north in Kaitaia there that gets above that. So we're a heating climate. That's really important. This is a climate that means we have to heat our homes. 20 degrees Celsius is a comfortable temperature for living. If we look at the graphs in the middle there, we see the mean high temperatures. Well, this is relevant because we're looking at what's going on at the highest points. And you can see that our main centers in the orange there in the middle They're only a few degrees apart. If we go to our mean low temperatures, yes, we've got some gaps. We've got Queenstown at nearly -2. That's also relevant because at those temperatures, mold doesn't grow. It doesn't grow outside. We know about the seasons of winter and things not growing. Life doesn't like to grow. It doesn't grow very well at those temperatures. Now, the mean relative humidity is often a bit of a surprise to people, especially people who live in Canterbury, where I live. They think Canterbury is nice and dry. But actually, the relative humidity of Canterbury, of Christchurch, is higher than Auckland. It's 85.1%. So that's outside. Obviously, it's not in homes, but that air is continually moving. We'll have a look at why this is irrelevant in a moment. So, New Zealand, it's damp and it's cool on average. This graph, a little bit strange type of a graph, but I'll explain what's going on with it. On the right-hand side, we can see an image of a petri dish, a petri dish that's been left on the windowsill for a couple of weeks. And nothing has been planted in there. The mold spores just come from the air. It sits on a food source. It's got the right temperature, right humidity, and stuff starts growing. That's what happens in nature. And let's have a look a little bit of why that happens. On the left-hand side, in the area that's now come up as red, you can see the number 1. That indicates 1 day. That's how long it takes to germinate. And if you look down the left-hand side of the graph, you'll see 65 to 100. That's a percentage of relative humidity. So between around 90 and just under 100, you get 1 day for germination for mold. But the temperature is also important. So if you look at the temperatures at the bottom of that graph, between 0 and 50, you can see it is somewhere between 20 and sort of mid-30s. It takes 1 day to germinate. So that means the mold spores, when they land on a food source, take 1 day before they start growing. They sit there for a little bit, absorb a bit of moisture, get a bit of food, and start growing. So all of your build sites, everything that's being built, you imagine how long it's exposed for before the doors are closed and you hand over the key. It's been covered in mold spores the whole time. It's got a high amount of relative humidity. The mold will start growing. Yes, we've got mold inhibitors, treated timbers. Treated timbers only last so long, especially if they're exposed. The first millimeter of that treatment will get washed off. Mold will feed on house dust, timber cellulose, and any other organic matter it can find. The red box there indicates our ambient relative humidity and our ambient temperatures. And we can see that it takes somewhere between 4 and 64 days for mold to germinate. So in terms of our building, you have to have got the job done in 3 days for the mold not to start growing on it. Okay, you've got to, and so it's impossible, right? But we've got to be aware of mold and understand it. So when we, in our designs, we can design it out. Now, the code meets the needs of the homeowner if it's used correctly. The acceptable solutions seem to fall short of the mark, and words like adequate certainly don't help. Now, with no verification method, how is the industry supposed to know that their decisions of design and material combination will be adequate? But there are free versions of thermal modeling tools available. Why aren't designers using them? This is where we go into our next poll.
Awesome, thanks Ben. And there's a lot to unpack there, so I'd expect there'd be a bunch of questions that come out of what Ben's presented. So for those of you online, please use the Q&A box for those, and then there's also a box there where we can send and will send you some of the links to the QR codes and bits and pieces during the presentation as well. So onwards with the poll. Let's go. What are your design strategies? Or maybe if you're a builder, what are you doing on site, as Ben was just talking about, to avoid mold? So we've got 5 options here. Are you using continuous mechanical ventilation, Are you working to eliminate thermal bridging? Do you have at least 5% of operable windows? D, do you use a vapor control layer? And E, all of the above. So what are your design strategies? What are your building practices? And I'm going to ask the people online to be entering their answers. And in the room, it's a little bit of an interesting one. Our panelists are going to come online in a moment too and discuss some of these. So let's go. So who thinks A? Who would choose A? Nobody. Who would choose B? Nobody. Who would choose E? All of the above. Oh, look at that. Okay, a few more hands up. Who would choose D? I'm going backwards now. Yep. And who would choose C? Okay, cool. Okay, so what we'll do is we're going to call on our panelists to have a quick discussion on this one. So if we can flick across to them, Richard and Simon. Hey, so Richard, you're not hearing us. I'm not sure why. Simon, have you got a comment maybe about the combination of all of those things?
Yeah, John. So from my perspective, I would go with A, B, and D. So I think it's pretty important to have some sort of mechanical ventilation to ensure that we're replacing the air. Secondly, we want to do away with those thermal bridges. And thirdly, we need to have ideally a vapor control and air barrier to make sure that we stop the moisture going into the cold places in the first place.
Richard, your audio is terrible. Let's just kill that for now, and we'll see if we can get that back online. So I think we're going to turn this way again, and maybe, Ben, you could make... Oh, we've got them back up? No? Oh, the poll results from online. I'm sorry. Okay. Oh, interesting. Okay, so 79% of people said E, all of the above. And then we've got a mix, pretty much the same percentages across the other ones. And if you were a part of our H1 presentation, Kat talked specifically about what we do as a company, Pro Clima. We have a dedicated vapor control layer, but she didn't talk about that. She talked about every other material that you're already designing with that is already airtight. So that's in the relationship with the airtightness and then the 5% operable windows. And I think you're going to dig into that in a wee bit. So if that was a bit confusing, Ben's going to unpack it all. So let's hand back to you, Ben. Thank you.
So I'm going to try and deconfuse them now.
Yeah, absolutely. That's your job.
I'll do my best. Thanks for that, John. Okay, so we're going to focus now on the design and how we can design out the problems with internal moisture. As we've seen, the code does know about mold. We understand it, it's there, and we also understand how it can be managed. But I wonder why we don't. Why don't we do it then? Why aren't we thinking, I wonder if this will get moldy? Two images here. This the one on the left is taken just a few weeks ago down in Christchurch. It's a new build, lovely suburb, right on the waterfront. It's actually so on the waterfront that it's had to be built 1.5 meters up, just in case the inundation zone that was marked on the map a few years ago is real, and it's a flood risk. Because it's so close to the water, it's going to have high relative humidities. You're going to get sea fogs rolling in, and you're going to get a lot of moisture in the air there. I asked the builder what he was going to insulate the steel beam with. He looked at me and said, oh, I don't know. I'll have a look at the plans. Nothing shown. Okay. He's got 6 millimeters between the steel beam and the top of that timber support there. So he's got to now figure out an insulation that's going to fit in there. So I said to him, I think you need to email your designer and ask them how they've mitigated the risks of E3. And I would record that, because at the end of the day, if this gets condensation on it, everyone's going to be pointing the finger. You don't want to be pointed at you, Mr. Builder, because it's not your money. You haven't got that kind of money. I suggested the builder contact his designer, make sure he recorded it, as I say. What we don't want to happen is that it looks like the image on the right-hand side here, where you've got a greying of the internal plasterboard on a home that's built with steel frames. Now, it was built to the specification, but they have 0.2, they've got a tiny sliver of insulation goes on the outside of a steel frame. And in Canterbury, it's clearly not adequate. The problems can be designed out, and they should be designed out. And in fact, they must be designed out. It's not It's not a choice, it's part of the building code. It needs to be adequate thermal resistance, adequate ventilation, and adequate temperature in all habitable spaces. It's in the code if it's applied correctly. Now, Kärcher window vacuums. You can tell when it's getting cold in New Zealand because Mitre 10 and other hardware stores advertise Kärcher window vacuums. I had no idea what they were until I came to New Zealand. Never seen one before. I don't think they get sold much in Germany. We all know what it's there for. It's to suck up the condensation on your windows. And why is it there? That's double glazing. Why should it have condensation on it? Well, it's because it's attached to something that is the third best conductor. It goes copper, gold, aluminium in terms of conduction. So we could have done it worse by using gold, admittedly, but we didn't. We used aluminium, and aluminium's a wonderful conductor. And as one member of a very reputable window association said, oh, but that's a free dehumidifier, is what he called that, which is fantastic. It's not a good insulator. Great conductor. Kärcher do so well in New Zealand because we have such terrible windows. If the Germans understood why we were doing it, they would just shake their heads. I know there's a few Germans in the room who would agree with me. Now, the same goes with steel. Admittedly, it's not as good a conductor, but it's doing exactly the same thing, but it's doing where you can't see it. If the steel is as cold as that aluminium, that's how much water it's got sitting on it. All right? Steel is great because it's easy to calculate, all right? It's readily available, but it is a conductor and a thermal bridge, and it needs to be handled very carefully. Now, a belt and braces approach doesn't always work. In this image here, we are looking into the ceiling space above a kitchen. That's a truss. We've got some pink bats below it, and we've actually above it, we've got some foil-backed PIR, all right? It was assembled as a warm roof design, but the owner of the home said, the kitchen's still cold. What can you do about it? Builder poked his head up. Silly, they've left out the insulation. And so he climbed up there and stuffed a whole load of insulation in. Now what that's done, it's created this perfect storm. The truss of the roof has become cold enough for water to condense on it because it's not getting the heat from below. That water condenses on the truss, and then, okay, the sun comes out, shines onto the roof, and normally that roof space would heat up. But it doesn't because the insulation is doing its job and isolating it. So the condensation just sits there. It sits at a nice, say, 15 degrees Celsius maybe, and a nice 85% relative humidity. And that's treated timber. So the treatment's failing because the mold is winning the battle. Mold will win. The treatment only slows it down. Eventually nature wins and the rot begins. Now, what can you do about it then? Pro Clima has done a study. There's a QR code for it here. It's a way of verifying your design. You can if you have a look at the QR code there, you'll get taken to our study website and you can download it. Now, the Pro Clima study, what it's done, it's analyzed different wall configurations, and it's looked at them both in winter and in summer. It's looked at them using WUFI. Now, WUFI stands for Warme und Feuchtigkeit Information. That means warmth and moisture information. Okay, that's what it is. It's not very creative, but it's German. We can't expect much. All right, it's a warmth and moisture information. What it does is it takes all the parameters of the materials involved and the climate zones of the area, puts them all together in a great big spreadsheet, chews them over for a little bit and spits out a result and says, yep, that'll work, or no, it won't. I'm sure there's a lot more to it than that, but I'm not a scientist. It's complex, but there are free ones available. These QR codes here show the Ubicus one. That's the one top left of your image, the QR code there. That's a free modeling tool. You can just go online, put some materials into it, I know our products are in there. You can test your wall with different climate temperatures. It's free, it's there. If you don't know, why not? It's your designers, builders, it's there. PHPP is a more complicated one that you can purchase. It's great to see you guys getting your phones out and taking those. We can help you afterwards if you can't grab them from here. It's there, it's free, why not use them? Okay, so here's a couple of details. I'll explain them to you. Most of you will be able to look at it and pick exactly what they are, but some people won't, and that's okay. The left-hand side, we've got a ridge, and there's a steel I-beam running through that ridge. The I-beam's there for structure. The designer has acknowledged that within that structure, I'm going to have to manage the temperature of that steel because they're aware of it. First of all, they're aware. Awareness is the first thing, isn't it? Yeah, that's a risk. All right, well, how am I going to do it? Now you've got to come up with a clever solution. Their solution is to insulate the coldest part of that steel from the external. They've insulated outside of the steel, possibly with a foam, a spray foam. The inside of the steel, where it's warmer, is not insulated. That's because they want the steel to be warm. They want the steel to be above the dew point. We've explained dew points. They don't want the condensation to form on that. The diagram on the left comes from Bob Burnett, the super home movement, doing a lot of work in Canterbury to improve the designs of homes. It's if you can't figure out what it is, we've got the top of a sliding door shown at the bottom of the picture there. Then we've got a steel beam as a lintel, and then we've got the second floor above it. And what they've done is they've brought the steel beam into the warm part, into the thermal envelope. Instead of it being out there where it's cold, they've brought it in with the purpose of keeping it warm. If it's warm, condensation won't form in it. It's just two ways, applying the same knowledge to design out thermal bridges, which is going to help with the risk of condensation on those steel beams. So we're going into our next poll, and we're going to have a look now at the ventilation.
Great, thanks, Ben. Okay, so why do we use, and this is great because this is a question which has come up from our online audience as well, or related, and we'll cover that too. Why do we use 5% of floor area as openable or operable windows for ventilation? So answer A, it's a nice round number that's easy to calculate. I like that one. B, 10% would be too much and windows would be more expensive. And C, it's based on international best practice. And D, we always have to have a Frank Lloyd Wright answer, as you already know from our quiz that's coming up tonight, but Frank Lloyd Wright used that ratio. So if you're online, you can fill in your answer to that one. And I'm going to ask our panelists to come on board in just a moment. And for our people in the room, what is your answer? What is your answer? Not what the right answer is. Who cares about the right answer? Who chose A? Let's just start at the top and go down this time. A, all right. So it's a nice round number, easy to calculate, which really means somebody made it up. Not a bad answer. B, 10% would be too much. Who chose that one? That's actually kind of connected to A. They're almost one and the same. All right, but I didn't say that. The panelists are going to talk about this in a minute. And C, it's based on international best practice. Who thinks that one? All right, there's going to be some bonus points for what year it was introduced. We'll get to that. And D, just a fun one. Frank Lloyd Wright made the rule. Frank Lloyd Wright made it up. Nobody chose that one? Anybody? All right. Okay. Online, let's have a look and see if we match what was online. So most of our people here said it's C, based on international best practice, and that is reflected there, so 69%. 17, I do like that answer, actually. I quite like the first two. So I'm going to hand across 5%, Frank Lloyd Wright, winner on the day. Not quite the winner, he came last. Okay, so let's hand across to Richard and Simon. What do you guys think about the combination maybe of A and B? And that I hope you've got those answers in front of you too. Richard, we're going to try you first. Let's see if your audio is going to run for you this time. I'm going to take you off mute.
Cool, you can hear me, John? Excellent. Yeah, that's interesting answers. Yeah, a few people with a bit of a sense of humour there answering D. Could have been him, who knows? And that's the whole thing. No one does know. I know Ben did a bit of a deep dive on this and couldn't find why we use 5%. It could be international best practice. It might not be. It might have just been a number that someone chose on the day when they had to, maybe they did it last thing on a Friday and then just had to put a number down before the weekend to sign off that part of the building code. But I mean, the point is, yeah, who does know? It's all a bit of a mystery. Let's take out the mystery. Let's make it calculable. Is that a word? I think I just made a word
up. Not bad. Yeah, so when you say make it calculable, let's use that. What do you mean by that? Can you just dig into that for a sec, please?
I guess, yeah, windows are unreliable. I mean, on a still day versus a windy day versus having one window open on one side of the house or a window open on both sides of the house, or if it's cold or hot or dusty or what, it's opening windows as the ventilation strategy is unreliable because it changes, you know. So I guess having a ventilation system that's running all the time, supplying the right amount of fresh air, you know, extracting air from the house, supplying fresh air to the house is something we can rely on and have working away no matter what the weather is, no matter who's in the house, no matter what's happening outside. So yeah, let's have a ventilation system which is a bit more reliable, I guess, is the key thing.
So, Simon, I'm not sure how familiar you are with Dr. Cara Rosemeyer's work. Her PhD was around what actually happens when you open windows, but hopefully you do know a wee bit about that, because I'm going to throw you the first question which came through from our audience earlier, and it is the 5% of operable window, what happens if those windows have stays on them? So kind of a bit of a lowball question in a way, which is nice, but do you want to attack that?
Yes, certainly, John. Thank you. So I did have a good catch up with Cara about this recently. And yeah, the issue is that, as you say, if you've got stays, you may have your stays limiting it only to opening, I don't know, is it 50 millimeters? Is it 100 millimeters? It's a pretty small opening. And according to Cara's research, the houses were certainly not getting a suitable amount of ventilation. And that's, of course, based on, you know, you're relying on wind pressure to actually move that through the house, and someone getting up and religiously going and opening and closing those windows on a regular basis, which just wasn't offering a regular and suitable solution.
All right, thank you. Sorry, I'd forgotten that you had interviewed Cara for your podcast, which is a shameless plug, which I wasn't planning on doing. Simon runs the Pro Clima podcast and interviewing all sorts of interesting people, like Joe Sturbrick. That one's already up online. There's a number of people who are already online. And are we talking about the other John? Are we allowed to do that? Give us a nod, Simon.
Yep.
I'm going to get myself in trouble. I've got you on mute. Give us a nod or a no.
Yes, John Straub next week, Wednesday.
Oh, okay. So I think tomorrow, the podcast where Simon interviews John Straub, Dr. John Straub, is being landed. Is that correct?
Next week, Tuesday, Wednesday, John.
It's true enough for today. And on that note, on your 5% operable windows, Ben, are you going to talk about the fact that people actually, you know, the wording there is operable, but people actually have to operate them, and that's the problem?
Absolutely.
I know Simon touched on that, but
I certainly am. There's no point in having a window if you don't open it, if you're going to ventilate, but how do you control that? How is that managed? So let's have a quick look. We can't really talk about E3 without discussing G4. Now, don't start reading that. I don't want you to all read it. I want you to just focus on a few key words. Now, G4 is all about ventilation, all right? And we'll see what it covers. Now, the objectives are clear, and we need to safeguard people. That's what this comes down to again, but also amenity, from loss of amenity and illness. We've got to look after the people who live in our homes. We've got the word adequate and the intended use, and we need the adequate, again, number of air changes. Now, who or what defines adequate air changes? Who knows? 5% pops up there. Yes, our magic 5%. Now, as I say, I did do a little bit of homework on this. It was brought in from the Europe in the 1940s. It's 5%. I did ask why 5%. Nobody knew why it was 5%. Nobody could tell me. I went to the guys at university. I emailed them. Why is it 5%? I don't know. My answer is this. 10% is really easy maths. Anyone could do 10% 200 or something like that, can't you? 200 square meters, right, 10%, 20. Oof, that's a lot. Let's make it 5. Yeah, all right, 5, done. There's no other answer for it, unless you've got a better one. I'm quite, yes.
Yeah, I think the answer is that you've got to have 10% of the floor area have windows, and so 5% was half of the window area.
And why do you have to have 10% of the floor area of windows? And why is that enough natural light? It depends what direction you're facing, surely. That's interesting. Thank you for adding that. That's great. So we've got this magic 5%. Now, we also have to look at the scope of this. And we're talking about cooktops, showers, must have mechanical and extract fans. And we are giving some parameters for that. So G4 does give us a little bit more to work on. By the way, if you're not sure what adequate means, the definition according to the building code is that it's adequate. That's actually what they've got written down. Adequate means adequate. It means adequate to achieve the objectives of the building code. So round you go. Oh, so what does the building code say? Oh, it's got to be adequate. So what is adequate? Adequate enough to not be moldy. Oh, well, prove it. Now, let's move on to understanding a little bit about relative humidity. We've got 3 charts here, and there's a QR code of where you can download or where you can get to this to find out how to calculate the dew point. Now, on the left-hand side, we've got an ideal setup. That's 20 degrees Celsius and around 50% relative humidity. It's also nice round numbers. They're easier to deal with. That gives us a dew point of 9 degrees Celsius. What does that mean? It means any surface that is 9 degrees Celsius in that build has the risk of condensation forming on it. Of course, anything that's below 9 degrees, that risk increases. So it's 9 degrees. So anything that's 9 degrees, so that might be the glass, might be the aluminium, might be the steel beam that's hidden behind the structure. All right. At 20 degrees and 70%, looking at the middle now. Now that's after we've done the cooking and had a shower. And everyone knows that when you have a shower, the mirror steams up. Why? It might not even, I mean, I was just staying in a hotel last night. I had a nice warm shower, mirror was all steamed up. Huh. I was thinking, that's interesting. Even though this room is at 20 degrees Celsius, the mirror must be at 20 degrees Celsius. I've got condensation forming. That's because the relative humidity has gone through the roof in the bathroom and it's condensed on everything. It's not just on the mirror, but it's at 14 degrees. That's where the dew point is in that mirror. That's where the dew point is in that situation. So after you've done the cooking, had a shower, hung up your washing, if you've got 70% relative humidity, 14 degrees is the dew point. So anything that's 14 degrees now has water on it. Now, more realistic scenario, 18 degrees Celsius, because most of us don't heat our homes to 20. 18 degrees Celsius. By the way, we don't, just in case you weren't aware, we have no aspect of the code that deals with what temperature a room must be unless it's a kindergarten or an old people's home. So the house that you build does not have a requirement for comfort. There's no clause for comfort. So 18 degrees Celsius, and it's a soggy 85% relative humidity. Okay, this is a bad scenario, but it means there's only 2 degrees difference in that, and 16 is where the dew point is. So hopefully this demonstrates the relationship. Now, anything within that build is going to have condensation on it, whether it's the studs, the dwangs, anything that's cool enough. And this is where the problems lie. And that's because we can't see it. We can see it on a mirror, we can wipe it with a towel, we can understand it, but you can't see it when it's behind a structure. We need to also understand what happens in the relationship of relative humidity a little bit more. ambient temperature and relative humidity sits around 10 degrees and 85%. We've seen that across the nation, around 10 degrees Celsius and 85% relative humidity. So that's the outside air shown there at the top. If we just warm that air up to 20 degrees Celsius, our relative humidity drops. Because the water amount hasn't actually changed. The amount of water in the air doesn't change. You're heating the air up, the air expands, so the relative humidity drops, which is great. This works in our favor because it means that if we can exchange the stale air with fresh filtered air and maintain a temperature, we can provide a safe and comfortable environment that is not always requiring a heating input. Funnily enough, that's exactly what a mechanical heat recovery ventilation system does. It keeps the air clean and it keeps it warm. The diagram on the left here shows how the heat exchanger within the mechanical heat recovery ventilation system. It is sucking air from the outside and it is passing over the air from the inside and they're exchanging their heat. So the cold air is getting warmed up and then it enters the house. It's going through filters in the process. So it's a heat exchanger and a filter. That's what it looks like in real life, attached to a wall. Now, it looks complicated and it looks expensive. And yes, of course, it does come with a cost. Everything that is progress has a price. But just like when we got anti-lock brakes for our cars, airbags, Bluetooth, all those things, they were expensive at first. Now they're standardized. And as we progress through our changes to our homes, they will become standardized. First part of the presentation, I showed you an image of a villa with a wood burning fire in it. And I had some arrows pointing from windows towards the wood burner. And that was the ventilation system that was used at the time. This is the updated version. What this does, it means it doesn't, first of all, it uses very little energy. It's like running an electric light. If you think it's too expensive to run, then it's also too expensive to have a 60-watt light bulb in your garage, okay? Because that's the amount of power that it uses. It's a very, very tiny power draw. It's like leaving a light on. What's happening here is the orange E's are the extract. Now they're being extracted out of in this case, we've got the kitchens, bottom right, bottom left, we've got the ensuite, top left, we've got the WC, the toilet, and then we've got the second bathroom and the laundry. And it's extracting 24 hours a day, low level extracting, just like we've got in here now. And I don't see anyone complaining about the noise of the extraction system. It's running all the time. We've got a supply air going into the living spaces. So what's happening there is the extract air is passing over the supply air, and the supply air is now warm and dry. And it's being supplied 24 hours a day, just gently, trickle feed. And by doing that, the air is constantly moving and it is constantly being maintained. The CO2 levels are being maintained and the temperature is being monitored. Now, putting that into a design, yep, this is where the homeowner and the architect thought it would be a good place to put it, nice and out the way, poke it in the corner. The circle shows the efficiency range. If you have to run the hoses for long distance, they lose their efficiency. Just like power loses efficacy, there's a good word for you, if it's running long distances. So best place to put it is more centrally. So if you don't design your home with this in mind, it becomes complicated. You need to create space for it. Placing it centrally means it can operate at maximum efficiency. And what does that look like? Well, as we say, there's always a cost for improving something. If it's designed in, you don't need to create more space for it. You can find the space within your build knowing that it's going to go in there. It might be an alcove, top left. It might be in the ceiling space, bottom left. Or in the center picture, you can see the ducting running through. Although it's a vaulted ceiling, they've created a service cavity for that. And the system can be placed in the laundry space or somewhere, but it needs to be placed centrally. Now, there's always a cost for improving something. But there's also a cost for doing things badly. Right? The big picture is that living with cheap, damp, mouldy homes, there's a price too. 30,000 children a year are hospitalised due to asthma in New Zealand. That's 30,000 children who are taken to hospital. They don't just have a little asthma attack and settle down once they're in hay. They go to hospital for their asthma. I wonder what the medical bill is for that. Surely there's a cost to that. And we've examined the context of New Zealand and the New Zealand climate. We've looked at how it relates to our building code. Now we need to do better because the code tells us to. Because our changing climate is demanding it. We can't just have fossil fuels burning in our homes like we used to. And it's because our children are getting sick. Now, to me, that alone should be reason enough for us to do something about it. We have briefly seen how to do it through intentional design, correct material choice, and by giving the naughty little Johnny in E3 a bit more attention. So, what can we use to do this? Well, we've seen there are tools that we can use, model, construct, methods to give accurate indication of where the systems will fail and how bad that failure will be. Now, wisdom, as a wise man once said, is the application of knowledge. We need to wise up and meet our potential.
Ben, thank you. Should we just give him a quick round of applause and then we'll get into some questions?
Thank you very much.
Great stuff. And that's the first lot of applause that we've done in this whole webinar series. Everything else has been online. Hey, Ben, I'm going to throw you a question that's a little bit of a toughie. You know what? No, I'm going to go to Simon, who's going to come online.
Good.
Oh, look at that. He's already there. And I'm going to ask Simon about the negative and positive pressure systems. Do they work? Are they better than just relying on windows for air change? I'm going to hand it across to you.
Thank you, John. So with regards to those two systems, with the positive pressure, the concern we have there is that we're drawing air from the roof space generally. We're pressurizing the building, and then the air can be forced to leak out through plug points and gaps and cracks through the actual fabric of the building and could condense on its route out. Negative pressure, on the other hand, we're drawing air from the wet areas of the building generally. There might be one in the passage as well. We can get a ducted system. And then we would need to have makeup air coming from another space. So we could install some passive vents, perhaps in the windows and things. So a ducted negative pressure running continuously can definitely assist with removing moisture from the home.
Cool. Okay, so that was just an answer to that question, not a specific answer to what you've covered with the balanced pressure system. So that's quite different. So good question. And Richard Hollard, I'm going to throw the last question before we close off. Do you know if MB are planning to update E3 to ensure we don't have the problems that have been highlighted in the presentation?
Cool, good question. Yeah, we've heard rumours and stories of MB working away at changes to the building code. I think it's it's just a live thing. It's always changing over the years. I guess it's a question of when, not if, things like an air tightness requirement, acceptable solutions to comply with E3, ventilation, mechanical ventilation systems, and that sort of thing come into the building code as standard. So most of the developed world, and MB would be looking at standards and practices in other developed countries. Most of the developed world, as we know, have some sort of requirement for energy efficiency in terms of air tightness and ventilation. We're likely to follow, but we don't know when that's going to happen. So I guess watch the space. Could happen in the next few years, might be 10 years.
Cool, thank you. Hey, we are out of time. We're going to shut off our online session at 4 o'clock, which it already has gone past that, 4:01. So just a quick thank you to Richard and Simon as our panelists, and to Ben again for the presentation today. Those people online, thanks for joining us. I hope that's been useful to you, and we'll see you again at another series, another time. Thank you.